Find the integral. Upstairs, 3t minus 2 quantity squared minus 5 plus 3 cubed root of t, that's what that notation means, over t. All right, now, what do we do? Well, we say, look, there's not a lot of integrals that we know. And so if it's not one of our 8, give or take, integrals that we know, we have to think of how to rewrite it. So a lot of integration comes to saying, well, let me get it down to something I know what to do. And so what we can do is algebra, right? We can square that out, gather terms, and simplify. Okay, so let's start by cleaning up the upstairs. This is the same as the integral. And when you square this out, so 3t minus 2 quantity squared, you can even do it on the side. We have space, we have time. So it's your a squared, which is 9t squared. Then your minus 6t, that's your minus 2ab. So that's going to become minus 12t, and then plus 4. Okay, so squaring that out, we have, just going to copy, 9t squared minus 12t plus 4 minus 5 plus 3. Now, cubed root of t, this is a great way to write it algebraically, but we want to write it calculus friendly. Now, when I say calculus friendly, friendly with the rules. So the rules are set up as like t to a power. And so we're going to rewrite this as t to the 1/3. All divide by t. All right. So again, so far we've done algebra. Now, what can we do? Well, one thing we can do is we can put the 4 and the 5 together. Okay, sure. No problem. But the other thing is we can divide. And so let's do both those things. So 9t squared over t gives us 9t. 12t over t gives us 12. Now 4 minus 5 is negative 1. And normally, we say most often you like to have t to the power, with one exception. T to the negative 1. We don't want to write that as t to the minus 1. We want that as 1 over t, because that's how our rule is written. So that becomes minus 1 over t. That's the 4 minus 5 over t. And then plus 3. Now, t to the 1/3 divided by t. Well, think of it as t to the 1/3 divided by t to the 1. Subtract the exponents. 1/3 minus 1. T to the minus 2/3. Good. Now, the next step is to integrate. And we're going to implicitly use something. Most of the time, we don't write the following down. But since we're new at this, right, we want to just sort of make sure we understand what's going on. Which is to say, hey, you see all these pluses and minuses here? What that allows you to do is to say, oh, let's break it up into several integrals, and then we can do each one individually. So like I said, normally this step right here that we're about to do, we don't write it down explicitly, but since it's our first one, we're still warming up. Let's go ahead and do that. So this becomes 9 integral of t dt minus 12 integral 1 dt minus the integral 1 over t dt plus 3 integral t to the minus 2/3 dt. So the idea is pulling it apart. And now we do each one separately. What's our generic rule? Well, our generic rule is the integral of t to some power dt is you add 1 to the exponent and then you divide by that. Now, the one exception is 1 over t. And in that case, you get log of t. And you'll notice that 1 over t to the minus 1, you can't divide by 0. So that's why we have to treat that separately. All right, so here we go. So we get 9. This is t to the 1. So it'll be t to the 2 over 2 minus 12. Now 1 you can think of as t to the 0 power. So t to the 0 would become t to the 1. Divide by 1 gets us 12. 1 over t, that was our exception. So minus log t. Now, I'm going to pause and say, depending on who you ask, they'll say, oh, wait, did you mean log t or did you mean log absolute value of t? And there's a discussion, and it tends to get a little bit complex. But I would say don't stress about it. If it makes you feel better throwing absolute values, you do you. And but for me, I'm okay with not including it. Okay, plus 3. Now, what's our new power? Add 1. Negative 2/3 plus 1, t to the positive 1/3, divide by 1/3. And of course, you need a c. You might say, wait, 1c? You had 4 integrals. How did 4 integrals just give you 1c? Don't you need 1 for every integral? Ah, ha, 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 ha. You see, c's are like sponges. They can absorb constants. So if you have 4 arbitrary constants and you add them together, the result is 4 arbitrary constants. So in other words, you can merge them. So you have 1c to rule them all. All right, now we're basically done, but let's go ahead, rewrite it, make it look a little bit nicer. So we can do things such as, say, 9 divided by 2. Well, we'll write that as 9/2 t squared minus 12t minus log t. And now this 1/3 comes up, and it becomes a 3 when you flip it over. 3 times 3 is 9. And if you wanted to, you could say, oh, I'll go back and rewrite that as cubed root of t, but you don't need to do that. But there we go. All right, one problem done. Ah, what a nice start. The acceleration of a particle at time t greater than 0 is given by the following. A of t, so a for acceleration, e to the power 2t subtract 36 divided by e to the t add 6 plus 3 over t squared. Now, given that the particle's velocity and location at time t equals 1 is e, find the position function s of t of the particle. Okay, so we have acceleration, we want position. How do we go from acceleration to position? Well, we do an intermediate step to get to velocity, and then we step again to get position. I may say, wait, what's this stepping you're talking about? That is antiderivatives. Because if you start with position, derivative gives you velocity, derivative of velocity gives you acceleration. So if you're going backwards, antiderivatives. So we say, okay. So we have a plan. We're going to start with acceleration, take 2 antiderivatives, we'll get position. Now there's a little bit of a wrinkle. As you do these antiderivatives, you get constants showing up. Like, do we have information to help us with those constants? Yes, and we'll come back and we'll revisit that when we get to that point. But first off, let's start with writing our acceleration. So we have a of t. That's e to the 2t minus 36 divided by e to the t plus 6 plus 3 over t squared. All right. Now, this does not look friendly. In other words, the pieces are not the kind of things that are on our list of things we can know how to integrate. So, before we take any antiderivatives or integration, and by the way, another way to say antiderivatives are integrates in different integrals, but we just say integration. And before we do that, we say, okay, let's think of how to rewrite it. Now, the 3 over t squared, that's not so bad. This is what makes us nervous, especially whenever you see a plus downstairs. That's a hard thing to overcome. So when you see a plus downstairs, you're like, ugh, what can we do to like be okay? And so we say, okay, well, is there anything we can do? Now looking at this, we start to get a little bit suspicious about these numbers here. you see there's a 6 and a 36. And like, wait a second, 6 and 36 are related. 6 squared is 36. What about e to the t and e to the 2t? Are they related in such a way? So for example, if you started with e to the t and were to square it, what would you get? In other words, let's check. E to the t squared is what? It's e to the 2t. And then all of a sudden it's like, oh, hold on. Let's write this down. So this is really e to the t squared minus, I'll write it as 6 squared over e to the t plus 6. And this last part, I'll just write that as 3t to the minus 2. Now, you might say, but what has that done? What do we see here? Something squared minus something squared. So in other words, it looks a lot like a squared minus b squared, because that's what it is. And we remember, because we've lived a good, clean calculus life, or I should say really a good, clean algebra life, when we have a squared minus b squared, that's the same as a minus b times a plus b. And so that says, hey, we can rewrite this first piece in a different way. So again, we still haven't taken any antiderivatives. We're just working on rewriting. And that becomes a lot of what happens when you're working with integration. It's just like, lots and lots of rewriting until you say, this is the right way to see it. All right. And now, huzzah! Now, this we can work with. This we can make progress on. All right, so we get e to the t minus 6 plus 3 t to the minus 2. That's our real acceleration function. And you're probably looking and saying, what do you mean? It's the same function. You're right, it is. But for calculus reasons, this is the one we want to use because it's the best. It's the most friendly to our rules. And so now we're ready. Okay, so let's start. We take an antiderivative. We get velocity. So velocity, antiderivative of e to the t, e to the t. Antiderivative of minus 6, minus 6t. Antiderivative of 3t to the minus 2, well, the 3 comes along for the ride. Then you'll add 1 to the exponent, t to the minus 1, divide by minus 1. That's the same as multiplying by minus 1. So that's e to the t. I forgot to put something. What else do we need? What else do we need here? Plus c. Right. Good. Good. I'm glad you remembered that. All right, so et minus 6t. I'm going to write this as minus 3 over t and plus the value c. Now, how do you find c? Well, you go back and you start saying, did they give us information? Did they give us a clue? And they did. They said, look, the velocity at time 1 is e. So we say, okay, let's plug in 1. So we can say the following. E is the velocity at time 1, which is equal to e minus 6 minus 3 plus c. Now notice the e's cancel here. And so what you really get is that c minus 9 equals 0, or c equals positive 9. Okay, so now let's update. So let's write our velocity using our known value for c. So our velocity function is e to the t minus 6t minus 3 divided by t plus 9. Okay, so we've successfully climbed up one step. Well, this is the problem so nice. We're going to do that twice. We're ready to climb another rung. So we're going to get to position s of t. All right, term by term. Antiderivative of e to the t, e to the t, minus 6. Antiderivative of t, t squared over 2. Then minus 3 is a constant. Antiderivative of 1 over t, log t. Antiderivative of 9, 9t. And then, don't forget a constant. Since we've already used c, we'll work our way up through the alphabet, d. Now, constants really can be any symbol, just conventionally you tend to start with c, d, and so forth. All right, and same idea. We say, hey, look, we're told that our location at time 1 is e. So that's another initial condition, and that's going to help us solve for d. Okay, so let's go ahead and run that computation. So we have that e, that's our position at time 1. So we plug in 1. That becomes e, and 6 divided by 2 makes 3, minus 3 log of 1. We'll come back and clean that up in a second. Plus 9 plus d. Now the e's cancel. Log of 1, 0, gone. And so when we simplify, this says, hey, if you take d and add 6, you get 0. 9 minus 3 is 6. Or d is negative 6. So our final answer is, S of t is, cleaning it up, e to the t minus 3t squared minus 3 log of t plus 9t minus 6. And there we go. We found our position function, exactly like we were asked to do. All right, so what's sort of some of the themes here? Before you try to do an antiderivative, make sure your function's as simple as it can be. Be kind to yourself. Remember, we love ourselves. We want ourselves to succeed. And so we're going to do the most we can to help us succeed. Also, remember to keep your constants. Every time you take an antiderivative, you get a constant, and use information to figure out what those constants are. All right, another problem done. Woohoo! Find the integral, or antiderivative, 3 sine 2 theta minus 4 cosine theta over cosine cubed theta d theta. Now, a comment we should make. We have seen integrals with x, we've seen integrals with t, we've seen integrals with theta. Same ideas. So that we have thetas, no problem. And we say, this is going to be a chance. We get to flex our trig muscles. Trig! Yeah! Who doesn't love a good trig problem? Trigonometry, those were some good old days. Now, when I look at this problem, and probably you'll see this too, something is like, that's weird. Notice the following. That's a 2 theta inside of there. But on the other hand, if we look in the other trig functions, we see a theta and a theta. So the insides aren't matching. It's like we have apples and other kinds of apples, right? They're not quite compatible. So we need to do something about that. So when we see the insides aren't matching, something needs to be done. So we say, okay, well, what can we do? And we say, well, the thing about trig is there's tons of trig identities. And that's a beautiful thing. It's also a challenging thing because it's like, there's a ton of trig identities. Which one do we use? And, but in this case, I think there's sort of a strong hint. There's one oddball, sine 2 theta. And then we say, there is something about sine 2 theta. It's called the double angle identity. And it says you can replace sine 2 theta by 2 sine theta cosine theta. And that would help us, right? Because then everything has a theta on the inside. So now it's all the same kind of apples. So let's do that and see where we're at. Okay, so this is the integral. 3 times 2 would be 6 sine theta cosine theta minus 4 cosine theta over cosine cubed theta. All right, good, good. Now, what can we do? Well, there's a couple things we can do, but let's start by there's two things, right? And I'm debating about which one to say first. One thing that we can do is everything has a cosine, and we can pull out and cancel one cosine. But there's another thing. The other thing is to say, hey, you know, when you look at this, I see something upstairs. I see a minus. And what that tells me is I can think about pulling it apart, because you're allowed to say, oh, let me think of this as two things instead of one big thing. And that's because it's upstairs. That's a good kind of subtraction. So let's suppose we do that. Let's think of this as two pieces. So 6 sine theta cosine cubed theta minus 4 cosine theta over cosine cubed theta. All right, I've already mentioned there's a lot of cosines, and so we'll cancel one out. So this will get us to cosine squared, and this will get us to, again, cosine squared. All right, now we start to think, is this on our list? No. Does that mean we're going to give up? No. Never give up. Never surrender. And we say, okay, well, what are things that we can integrate with trig? So essentially, if you think about things we can integrate, so I'm going to call this trig we can integrate. It's a fairly short list right now. And we can do sine, cosine, secant squared. I should throw some thetas in here. And secant tangent. Those are the list of things we can integrate. So if we have trig, at this point in time, we're like, is it one of these four? If it's not, can I make it one of these four? And so with that mindset, we start to say, sine and cosine, not looking too promising. But wait a second, secant. What's another way to think of secant? Secant is 1 over cosine. Like, oh, that might be handy. Okay, so secant theta, it's 1 over cosine. And what about tangent? Well, tangent is sine over cosine. So we're like, oh. So here, when we have a 1 over cosine squared, what happens? That becomes a secant squared. Now here, you might say, aha, so this becomes like sine theta times secant squared. True, but that's not on our list. But notice, we say, oh, notice if you multiply these together, you get 1 sine upstairs and 2 cosines downstairs. So you could say, hey, this looks a lot like secant theta tangent theta, because it is. It's just written in a different way. So this is equivalent to the following. This is the integral of 6 secant theta tangent theta minus 4 secant squared theta. And now we're in good shape. These are on our list of things we can integrate. And constants we're okay with. Okay, so we get what? 6. The integral of secant theta tangent theta is secant theta. All right, good. And minus 4. Integral of secant squared theta is tangent theta. Yes. Good. Wonderful. And of course, because we want all the points, don't forget plus c. All right, and there we go. So fun practice with trig and learning to say, hey, let's rewrite. And the nice thing about trig is right now we know our goal. These are our goals. You say, look, if you have a trig, this is what you're shooting for. And so you kind of have a mindset, how can I manipulate this expression to make it look like some combination of these? All right, well, we're doing great. Let's keep it up. Find a function y equals f of x with the following properties. The first property, d squared y dx squared, second derivative, equals 6x, and second property. The graph passes through the point 2, 4 and has a horizontal tangent at that point. Okay, so let's think about ways we can express these. Now here, this says the second derivative is 6x. So we could really say, f double prime of x equals 6x. That's another way to write that. Now, this part is giving us information about the function. So, what do we know? Well, we know it passes through the point 2, 4. So, that says if you plug 2 into your function, you're going to get 4 out. Okay, so that's what that means. And has a horizontal tangent line at that point. Now, what does it mean to have a horizontal tangent line? We have a flat tangent line. It's not going up, not going down, it's flat. Okay, so flat. When do we have a flat horizontal tangent line? Well, that says something about our slope. Slope is 0. Okay, so horizontal, slope is 0. And so since that's at that point, that must mean the slope, which comes from the derivative at 2, must be 0. So we're like, oh, so it's like you give me the second derivative and some initial conditions, find the function. All right, so now we understand the problem. We'll go through and work our way up. So we have f double prime of x equals 6x. So we're ready to do round 1, taking an integration or taking antiderivatives. So antiderivative of 6x. Add 1 to the exponent, will give you an x squared. Then you have 6 divided by 2. And this really is 3x squared, and don't forget your constant c. We know information about the derivative. So we can say 0 is equal to the derivative at 2. Well, that's equal to, plug in 2, we'll get 3 times 2 squared plus c. Well, that's 12 plus c, so that tells us that c is negative 12. Okay, so we really have that f prime of x is 3x squared minus 12. All right, well, we're almost there, right? We started with an f double prime, now we're to an f prime. One more step, and we'll be home free. Okay, so another integral, another antiderivative. So here we go, f of x. Okay, add 1 to the exponent, x cubed. Don't forget to divide. Then integral of 12, 12x, and then another constant. And we're going to use a different symbol. It's a different constant, so it deserves a different symbol. All right, so that's really x cubed minus 12x plus some constant, but we have information. So we're going to use it. So we say, well, 4 equals f of 2. F of 2, 2 cubed is 8. 12 times 2, 24. And then our constant. Well, okay, so we can add 24, subtract 8. And if you add 24 and subtract 8, what's going to happen? Do it to both sides. We're going to get just the constant d on one side. 4 plus 24 is 28. 28 subtract 8 is 20. So we get that f of x is equal to x cubed minus 12x plus 20. And what do we have? We now have f of x. What do we do next? We celebrate. Woohoo! We found it. We found the function. Do, 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 do. We're gonna give points, right? Because that's what it asked us to find. We found the function. So we box it, and we happily move along to our next problem. Given that v of t, velocity, is 21 minus 4t over t squared plus 9, and that's our velocity in centimeters per second, estimate the displacement the particle has traveled from time 0 to 4 using a Riemann sum with 4 equally spaced intervals and using the right endpoints of each interval. Include units with your answer. Okay, so first off, we're doing a Riemann sum, so it's an approximation. And Riemann sums we can think of like, hey, isn't that kind of like adding up a bunch of rectangles? Yes, if you think of it as finding area. But really, Riemann sums and integration in particular is about finding totals. You may say, okay, so in this case, what's the total? Well, the total is the displacement. And so displacement is really just another way of saying how much have you moved. So if you were to use the language in terms of the position function, s of 4 minus s of 0, this is how much you have moved. So we don't really know where we are at time 4 or at time 0. We're trying to compare. Okay, so how do you find how much you move? Well, you take a velocity times the time, and that gives you an answer, assuming your velocity is constant. When your velocity is changing, you say, well, cut things up in little tiny time segments, and then your velocity never changes much in those tiny segments. Then you say, okay, how much do I move in each little piece? And you add it up. Now, it's not perfect, but it can get there if you use more and more pieces. And that's one of the great stories that we have. All right, so here's our idea. Well, we're going to have time 0 to 4. So let's sketch 0 to 4. And we say, well, how many pieces? 4. So, and they're equally spaced. So we say, okay, so we're going to chop this up into 4 equal parts. And it's not too hard to think, how do you chop 0 to 4 into 4 equal parts? Well, you go 0, 1, 2, 3, 4. All right, well, that wasn't so bad. No, it's not bad at all. Now, well, what are we going to do? Well, we're going to estimate how far did we travel in each segment. Now, what do we need? Well, we need to have a length of time, and so each segment is 1 second in time. But then we also need to have a velocity attached to that. So that says, what velocity should we be using between 0 and 1? Because it's not going to be exactly constant. So we have to pick. And that's where this word comes in. Right. It says, okay, for the first interval, choose the time 1. What's your velocity? That's going to be the velocity. We're going to pretend like we're going for the whole interval. Similarly for 1 to 2, 2 to 3, 3 to 4. So we get that our displacement, which is our distance we've moved, or how much we've moved, is the following. So our displacement is going to be approximately, and it's okay to say it's an approximation, because why? Because we're estimating. We're not guaranteeing that the displacement is this. We're saying it's an estimation. Okay, so we have our speed at time 1 times 1 second. So that's estimating how much from 0 to 1, plus our speed at time 2 times 1 second, how much from 1 to 2. Our speed at time 3 times 1 second, okay, that's from 2 to 3. And our speed at time 4 times 1 second. All right, so, well, what's our velocity at time 1? Plug it in. We get 21, subtract 4, 17 over 10, plus, plug in 2, 21 minus 8, 13, divide by 4 plus 9, 13, plus, and these are all times 1, so times 1 doesn't do much, so that's why I'm not stressing too much about writing down times 1 times 1. All right, v of 3, 21 minus 12 is 9. And then 9 plus 9 is 18. And then plug in 4. 21 minus 16 is 5. And then 16 plus 9 is 25. All right, well, we can clean this up a little bit. This is 17 over 10. 13 over 13 is 1. 9 over 18 is a half. 5 over 25 is 1/5. Common denominator would be a tenth. Okay, so 17 over 10, 10 over 10, 5 over 10, 2 over 10. Okay, so 17 plus 10 plus 5 plus 2 is another 17. So that gets us 34 over 10. Good. And that's our answer. Right? Right? Wait, there's a suspicious gap. What did we do wrong? Well, no, it's not that we did anything wrong. But what else do we need to do? It says, include units. Okay. And so we say, well, displacement, that's how far we've traveled. That's really about distance. Our units are centimeters per second for velocity, which means our distance measurement is centimeters. And so there we go. 34 over 10 centimeters. If you're an engineer, that's the same as 3.4000 centimeters. So that gives you the precision that you might need. But all right, good. A nice warm-up problem for Riemann sums. Use a Riemann sum to approximate the area under the curve y equals the square root of 30 plus 7x over 4 for x going from 4 to 16 by partitioning the interval into 3 subintervals of equal length and evaluating y at the subinterval midpoint. Okay, well, let's see what's going on here. So let's start by drawing our intervals, right? We have 4 to 16. Now, we need to cut this into 3 equal parts. And we say, okay, well, think of how to do that. How far apart are we if we go from 4 to 16? So from 4 to 16, we are distance 12. Yes? 16 minus 4. Now divide that by 3. So from 4 to 16, 12 divided by 3 says make your steps in sizes of 4. So 4 plus 4 is 8, plus 4 is 12, and plus 4 is again 16. So those are our 3 intervals. Now, a couple of things we should note. Our widths are pretty wide here. So here we have a width of 4. And we're actually going to have them all be width of 4. But again, I just want to emphasize we have our widths. Now, which point do we pick? Well, the middle point, the midpoint. So I say, okay, well, what's halfway between 4 and 8? Halfway between 4 and 8 is 6. Halfway between 8 and 12, 10. Halfway between 12 and 16, 14. Now, you can think of it as either, oh, if I step 4 to go the whole way, I'll step 2 to go half the way. Another way to do it is just say, I know my ends, and take the average, add them up, divide by 2. Okay, so our area, because we're told to find an approximation for area, so our area is approximately our function, and even though this doesn't say function, I'll say our function at 6 times 4 plus our function at 10 times 4 plus our function at 14 times 4. So the only thing that's left from here is we've got to find these values. So the setup for Riemann sums is fairly straightforward. Not a lot of surprises. We just have to be very careful in making sure we evaluate things correctly. Okay, so let's start with f of 6. So 7 times 6, 42. Some say that's the answer to life, the universe, and everything. But for us, it's 42. 42 plus 30 makes 72. And 72 divided by 4, do we know that? 72 divided by 4, it is 18. All right. So we have the square root of 18 times 4. 10. Oh, that won't be too bad. 30 plus 70 is 100. 100 divided by 4 is 25. All right, we'll come back and visit that one again. Now this one, 14. Whew, okay, now this one we probably should work a little bit on. 7 times 14, well, that's 70 plus 28, that's 98. 98 plus 30, that's 128. Now, for all you lovers of powers of 2, you might recognize 128. It's 2 to the 7th power. All right, and 128 divided by 4 is 32. So this becomes the square root of 32 times 4. Well, we can go a little bit further, and so let's do that. So 18 is 9 times 2. 25 is 25. That's already pretty friendly. They might say, wait, why did you do 9 times 2? Well, I'm looking for squares because I have square roots. And what about 32? That's 16 times 2. Again, 16 is a square, very friendly with square roots. So this will become 3 times square root of 2 times 4. So this is 12 square root of 2. Square root of 9 is 3 times 4. Here, square root of 25, 5 times 4, 20. Square root of 16 is 4 times another 4, gets us back to 16, square root of 2. So we end up with 20 plus 16 plus 12 is 28 root 2. And there we go. That's it. We found it. Woohoo! Nice! Consider the following table, which gives information about the function f of x at some points. So we have x and f of x from 0 through 9. And we don't have all the points, just some, just at the whole numbers. So we don't know what f of x is doing in between. It could be doing crazy stuff, but generally the assumption is it's not too crazy. All right, now what are we asked? Use this information to approximate the area under the curve for the function g of x, and g of x is formed from x, f of x times f of x minus 1, from x equals 1 to x equals 9, using a Riemann sum by partitioning the interval into 4 subintervals of equal length and evaluating g at the right endpoint of each subinterval. All right, so let's think about what's happening here. So we're going to take our interval from 1 to 9, and we're going to chop it up into 4 equal pieces. So cut it in half and cut it in half again. And it's not too hard to figure out how do you go from 1 to 9. Well, to get from 1 to 9, you go 8. And if we're doing 4 equal parts, that means we have to take steps of 2. So our intervals are 1 to 3, 3 to 5, 5 to 7, 7 to 9. And of course, we should make a note. What are our widths? So we have width 2. And that's true for every single subinterval. All right, so now we have our widths. And since we have our widths about us, we should find our heights. So that comes into play by saying, which point do we look at? The right. So for the interval from 1 to 3, we're going to look to 3. From 3 to 5, look to 5. 5 to 7, look to 7. And from 7 to 9, look to 9. So our area is approximately going to be the function at 3, g of 3, we'll figure out what that is in a second, times width of 2, plus the function at 5, that's our height, times our width 2, plus our function at 7, which is our height, times our width 2, plus our function at 9, times our height 2. In general, you should say, hey, if I'm breaking into 4 parts, I need to have 4 terms. If you have 5 terms, something's wrong. If If you have 3 terms, something's wrong. 4, just right. All right, well, now how do we find these? We say, well, there's a rule. We know what g of x is. So according to this is going to be g of 3 would be 3 times f of 3 times f of 2 times, don't forget that 2, plus g of 5 would be 5 times f of 5 times f of 4, don't forget that 2. G of 7, well, that would be 7 times f of 7 times f of 6. And don't forget that 2. And g of 9 is going to be 9 times f of 9 times f of 8. And don't forget that 2. Okay, so we're unraveling here. How do we get the f's? From the table. So we get 3 times 5 times 4 times 2. Right? F of 3 is 5, f of 2 is 4. Plus 5 times negative 1 times 3 times 2. Because f of 5 is negative 1, f of 4 is 3. Plus 7 times 2, f of 7 times negative 2, f of 6 times 2. Plus 9 times f of 9, which is 1, times f of 8, which is 5, times 2. All right, well, 2 times 5 is 10. 3 times 4 is 12. 12 times 10 is 120. 2 times 5 is 10. And then times 3 is 30. And then don't forget we're subtracting. So subtract 30. 2 times 2 times 2 is 8. There's a minus. And 7. 7 times 8. Now, I've never told people this, but 7 times 8 was always challenging for me. When I was a kid, I was like, oh, please, don't ask me 7 times 8, because I knew that was the one I didn't know by heart, so I always got nervous. But then I realized, wait, if I'm always getting nervous about 7 times 8, I just have to memorize it. 56, and life is good. All right, last one. 2 times 5, 10, times 9, 90. All right, well, how can we put this all together? Well, we have 210 is 120 plus 90. And then subtract 30, that's 180. All right, we can do that. And then subtract 56. 180 subtract 56 would be 124. And there we go. 124. Wow. What a number. What a number. And is it right? Who knows? It's an estimate. We don't know what the function does, but we know what the procedure tells us to do. And we followed the procedure correctly. And so, yeah, we're pretty happy with the answer. All right, good, good. Use a Riemann sum with 6 equal-sized intervals and left endpoints to approximate the area under the curve of g of x equals sine pi thirds x on the interval 0 to 3. All right, so, well, let's figure out what's going on. So let's mark our interval. So we're going 0 to 3, and now we're actually going in step sizes of 1/2, right? Because how far apart is it? You know, if you start from 0 to 3, that's a distance of 3. And we've got to take 6 steps to get there. So that says you take, 3 minus 0, divide by 6. That says your step sizes have to be 1/2. So if we split this up, we get 1/2, 1, 3/2, 2, 5/2, 3. All right. And so this is going to be a little bit bigger than our previous sums because we're going to have 6 terms. 6 terms! All right, so all our widths are 1/2. We're going to make a note of that. Now, the other thing that might be helpful for us is let's talk about the sine function. And so in particular, we're going to mark some values for theta here. And what values for theta do we know? Well, we can start with some very simple angles and say we know 0. Sine of 0, 0. Okay, how about pi over 6? Pi over 6, sine of pi over 6, 1/2. How about pi over 4? That's square root of 2/2. All right, how about pi over 3? That's square root of 3/2. All right, how about pi over 2? That's 1. They say, great, we're done, right? Well, we can keep going because we're going to get all the way. If you think about it, 3 times pi thirds is pi. So we want to get all the way. Okay, so we say, okay, what comes after pi over 2? Well, that would be 2 pi over 3. And that's also square root of 3/2. And you're like, wait, what? How? Okay, so let's look at the picture here. So I'm just interested between 0 to pi, because that's, I'm plugging in x, the inside becomes sine of 0 up to sine of pi. Now recall, sine equals y values. That's the way that we define sine on a unit circle. So if this is our unit circle, we say, okay, so pi thirds would be this angle, 2 pi thirds would be this angle. And notice, they're the same height. So that's why they have the same value. Okay, and now as we keep moving along, the next angle of interest is 3 pi over 4, and that's square root of 2 over 2. 5 pi over 6, and that's 1 over 2. So 5 pi over 6, again, if here's your pi over 6, 5 pi over 6 is exactly the same height. So the same value. And then we get up to pi, and sine of pi is 0. Okay, so there's a quick recap unit circle. And now let's plug this all in and see what happens. Okay, so remember, we're after left endpoints, so we're going to be going to the left sides. All right, so our area is approximately g of 0, height, times a half. Height, width, plus g of a half, times a half, plus g of 1, times a half, plus g of 3/2, times a half, plus g of 2, times a half, plus g of 5/2, times a half. Let's check. Do we have 1, 2, 3, 4, 5, 6? We do. All right, good. Whew. We got them all. Now, what does this become? Well, g of 0 is sine of 0. So this is sine of 0 times a half. Now, one thing you can do, and people often do, is factor out the half. If you want to, great. If you don't, great. We're all friends here. Pi thirds times a half, pi 6. So pi 6 times a half. Pi thirds times 1 is pi thirds. So sine of pi thirds times a half. Pi thirds times 3/2 is pi halves. So sine of pi halves times 1/2. 2 times pi thirds is sine 2 pi thirds times a half. 5/2 times pi thirds is 5 pi over 6 times a half. All right, now here we go. Sine of 0, 0. Okay, so this is 0 times a half. Sine of pi over 6, a half times a half. Sine of pi over 3, square root of 3 over 2 times a half. Pi over 2, 1 times a half. 2 pi over 3, square root of 3 over 2 times a half. Sine of 5 pi over 6 is a half times a half. All right, let's just check. Okay, we still have 6 terms. That's a good sign. Now, 0 times a half, that's easy, 0. And, all right, so we have here a quarter. Here's a half. Here's a quarter. If we put those together, a quarter plus a quarter is a half plus a half makes 1. Plus. Now, here we have square root of 3 over 4, square root of 3 over 4, and so you can say 1/4 square root of 3, 1/4 square root of 3. Put those together, you get 1/2 square root of 3. And then we're done, right? We've got the 0. We got the 3 terms without square root of 3. There's the 2 terms with square root of 3. And so there we go. There's our estimate for the area under this curve. Under the curve sine of pi thirds x from the interval 0 to 3. 1 plus a half root 3. Is it exact? No. Is it an approximation? Sure. That's the whole point. We're doing approximations. All right. Great. We did it. Woohoo! Nice. Find the antiderivative, or the integral, 2x squared over x squared plus 1 minus 6 over the 5th root of x cubed. Okay. Whew. All right. Now, this last term, this is just, looks hard, but then you realize, oh, it's just written in a non-calculus friendly way. We can do a couple of things. The 6 is a constant, then we have x to a power. Because it's downstairs, it's a negative power. And then we have 3, because it's raised to the 3rd power, and this is the 5th root. So that means divide by 5. And now it's like, yeah, okay. That we can work with. All right, now, the more interesting thing is the first term. What do we do about this one? Now, there's a challenge here, insofar as we do have a plus, but it's in the wrong place. This is a bad plus. In other words, it's a plus that's downstairs. We don't like those. Those are not friendly to us. And so we have to think about how do we handle it. Now, there is a nice rule, and so let's write that down, because it's like x squared plus 1 downstairs. That sounds familiar, almost like we should know that. And that's because we should. And the integral of 1 over x squared plus 1 is equal to arctangent of x. And there are some people who really love arctangent. They just go crazy over it. And I'm one of those people. I don't hide it. I like arctangent. It's a great function. But, of course, you have to figure out, how do we handle it? The issue here is we don't have 1, we have 2x squared. Yeah. So that's bothersome. So there's a couple ways to do it. But one of them is sort of like a fun, clever thing that's like, how would you know how to do that? The other way is like, oh, that doesn't sound exciting. Turns out they're the same thing. So here's the fun, clever thing you can do. You can say, well, the top almost looks like x squared plus 1. Like the 2 is a 2. Constants we don't worry about. X squared is not far off from x squared plus 1. How close is x squared to x squared plus 1? It's 1 away, right? So here's sort of the great, oh, what we can do here is we can say, let's think of it as, again, we'll pull the 2 out, and we have x squared over x squared plus 1. You're like, that's a very suspicious gap you've written there, Steve. And you say, well, we knew that x squared is really close to x squared plus 1. It's 1 away. But you can't just throw in plus 1s. You've got to somehow balance it. So you have to find a way to say it's equivalent to what we did before. And the rule of thumb is there's 2 things you can do. You can multiply by something that's 1, or you can add something that's 0. Well, since we're adding, let's add 0. How do you add 0? Well, if you add 1, subtract 1 right away. And they're like, cool, you've added 0. But actually what we've done is we've added a well-chosen 0. We have chosen wisely. Why? Well, think of it now as you have two pieces. So one of the pieces is x squared plus 1, and the other is minus 1. So let's rewrite our integral. So we have 2, and I'm now going to use the minus here. It's a good minus because it's upstairs. Upstairs, those are the good kind. Those are the ones we can separate. So we really have 2 x squared plus 1 over x squared plus 1 minus 1 over x squared plus 1. And you can go back and say, yeah, that's equivalent to 2x squared. Don't forget we have this other term on the end, 6x to the minus 3/5, and we're integrating dx. If I haven't said it yet, let me say it now. Notation is important. Always make sure to include this on the end. And you're probably just like, does it really matter? Don't we know what we mean? At this stage, it doesn't feel like it matters, but there will come a day, especially when you hit multivariable calculus, there will come a day when you're like, it matters. It matters a lot. So get into the habit now. Good habits start when we're young. All right, now our great, wonderful thing is this 1 over x squared plus 1. We like this because we have a rule. And the x squared plus 1 over x squared plus 1, we like that too because we say, hey, this is 1. So we really have 2 minus 2 times 1 over x squared plus 1. Minus 2 times 1 over x squared plus 1. I can write x squared plus 1 minus 6x to the minus 3/5 dx. All right, and now we're ready. Term by term, integral of 2, 2x, minus 2, integral of 1 over x squared plus 1, just look up there, arctangent of x. Nice! Then minus 6, add 1 to your power, negative 3/5 plus 1 will become positive 2/5, then flip it over. So it's like dividing by 2/5, but that's the same as multiply by 5/2. And now don't forget your plus c. You want to get all those points. Make sure you add your c's. All right, so that's 2x minus 2 arctangent of x. And 6 divided by 2 is 3 times 5 makes 15. And if you wanted to, you could rewrite x to 2/5 in a very similar form. Why not? Just for fun. The 5th root of x squared. Toss in a plus c. Life is good. We got our points. Woohoo! Nice. All right. So anyways, this is the magic of adding 0. Now, if this seems like that's a trick, isn't there a better way? The answer is coming up in the next problem. So stay tuned. Find the integral z minus 2 times 4z squared plus z plus 6 divided by z squared plus 1 dz. Well, what are we going to do? We're going to do algebra. Simplify with algebra. All right. Oh yeah, it's an algebra problem. Okay, so the thing is, there's a lot we have to do. Now, one thing that's making us a little bit nervous, and we probably can spot it right away, is that +1 downstairs. But what does that mean? It means we're going to have to do some work. That's all right. We know in the back of our head that we say, you know, there's a nice fact. We wrote it down before, but it's such a nice fact, it bears repeating. 1 over z squared plus 1 dz, we can find that antiderivative, arctangent of z plus c. Okay, so what's our algebra? Well, first off, we're going to work on the numerator. We're going to expand it. And it's a lot like foiling, but because it's a little bit more than FOIL, right? Because it's the philosophy of FOIL. The philosophy of FOIL says take each possible from the first, combine it with each possible from the second. And so, what do we have? Well, we get the following. This is going to be equal to the integral. So we'll start here. Z times 4z squared, 4z cubed. Z times z, z squared. 6 times z, 6z. Minus 2 times 4z squared, minus 8z squared. Minus 2 times z, minus 2z. Minus 2 times 6, minus 12. All of that's the upstairs. Downstairs hasn't changed. And there we go. So we've expanded. Now we'll gather. Okay, so gathering. What do we have? Well, there's only one z cubed term, so that's pretty easy. Z squared minus 8z squared minus 7z squared. Plus 6z minus 2z plus 4z and minus 12. All right, now here's our issue. We have a lot of stuff. We just want like a number. Number above z squared plus 1 we can handle. Anything beyond that we can't. So how do we proceed? What's the next algebra thing for us to do? The next algebra thing for us to do is divide. We're going to carry out long division. Divide one polynomial into another polynomial. And you're probably like, no! I thought I'd never have to do that again. But you know, it's not so scary. It's okay. We'll get through it. And it's a preview of some of the fun things that await for us in next semester. Calculus 2. Good times ahead. Okay, so here we go. We're dividing by z squared plus 1. So we'll write that down. Z squared plus 1. Divide it into, and now copy this down. 4z cubed minus 7z squared plus 4z minus 12. Now, on a side note, if we were missing things, so for example, say there had been a 0z, then we would put a 0z here, right? We want to make sure we have everything accounted for. It just makes for easier bookkeeping. Now, here's the great thing about division, is you don't have to think of the whole thing all at once. Focus on a very, very simple question. And you look at your leading powers. So in this case, z squared and 4z cubed. And your very simple question is, what do I need to multiply z squared by to get 4z cubed? That's not a bad question. What's the answer? 4z. Okay, great. We write it down. 4z. Now, here's the next step. We're going to update what we have left to figure out. So we say, well, part of our answer involves a 4z, but that affects the rest of the polynomial. So we say take 4z times z squared plus 1. So that would be 4z cubed, and then 4z. And we're going to subtract. And because, we say, look, 4z really captures more than just the leading term, it captures other terms as well. So we're updating the polynomial that we need to consider. Now in this case, we got lucky in that both terms canceled out. Doesn't always happen, but that's okay. Let's not complain. Minus 7z squared minus 12. All right, now we're ready to repeat the same question we had before. Okay, so we look at our leading terms. I'll switch colors here just to emphasize different question. And all right, there we go. Bright orange. Z squared minus 7z squared. What do you need to multiply z squared by to get minus 7z squared? The answer? Minus 7. Okay, cool. So you're going to put down minus 7. And again, multiply minus 7 through it to update. So minus 7 z squared minus 7 and subtract. So in other words, the 4z minus 7, it changes what you have left to account for. Here we get cancellation. By design, these first terms will always cancel. If they didn't, you did it wrong. Minus 12 subtract minus 7. It's like minus 12 plus 7, which gives us negative 5. Now here we stop. Why do we stop? Well, look, the power here, z squared, is bigger than the power of 5. So what does this tell us? Okay, so here's what this tells us. We have the following. This is equal to the integral. The long division says, okay, take the 4z minus 7, and that has nothing below it. You've divided it out, plus the remainder, negative 5, and then divide by what you divide by, z squared plus 1 dz. Okay, so what you have, your remainder, what you divide by. Okay, so now we're pretty much ready to write down our answer, because everything is okay now. The integral of 4z, there's no problems. There's nothing below it. So add 1 to the power. That would be z squared divided by 2, 2z squared. Integral of minus 7, minus 7z. Minus 5 is a constant. Then the integral of 1 over z squared plus 1 is arctangent of z. And then we finish off by plus c. And there we go. That's it. All right, so there's the moral. If you see stuff above z squared plus 1, that's z squared or higher, you can carry out long division. And in fact, if you went back to problem 9, that's what was happening. When you had 2z squared over z squared plus 1, you were secretly doing long division. You just didn't know that you were. But all right, cool. A nice way to finish a set of problems. Good, clean algebra fun. Because if you've lived a good, clean algebra life, calculus is really kind of interesting and enjoyable. So thank you. Thank you for coming. Thank you for joining me on the ride and doing the practice and putting in the time. I know you can do this. This is worth it to know these things, and so that you can do wonderful and go on and do great and glorious things. I hope to see you again. Bye.